Welcome to the second season of Tech and AI. Enjoy the episode, and please subscribe. Thank you.
I want you to stop for a second right now and just think about what is happening quietly inside your pocket or maybe in your backpack sitting next to you.
Oh, yeah. It's actually kind of wild when you really break it down.
Right. I mean, your phone might just be sitting there, but it's quietly organizing your massive photo library. It's recognizing faces, grouping them together. Your laptop might look like it's asleep, but it's ready to wake up instantly, maybe even running a local language model in the background to help you draft an email the second you open the lid.
It really is incredible when you pause to think about it. I mean, we have these small consoles that can render photorealistic 3D worlds in real time. We have phones that can translate spoken language on the fly. It's magic.
Yeah.
It is practically magic.
It totally feels like magic. But here's the problem I've been running into lately and why we're doing this deep dive today. I was actually standing in an electronics store yesterday looking at a literal wall of laptops. And honestly, I felt like I needed a degree in electrical engineering just to buy a machine to write emails and watch videos on.
Yeah, it's gotten incredibly noisy, hasn't it?
It's barely English anymore. It used to be so simple. You'd go and say, okay, get the i7, it's faster than the i5, done, easy. But now I'm seeing all these stickers for AI PCs and something called TOPS, and then there's this new acronym, NPU, plastered everywhere next to the CPU and the GPU. It honestly feels like marketing departments are just throwing alphabet soup at us to justify raising prices.
It definitely feels that way.
Yeah.
I completely get that. But for once, and I mean this sincerely, this isn't just marketing fluff. That alphabet soup, specifically the rise of the NPU, it actually marks the biggest shift in computer architecture since, well, maybe since we started putting dedicated graphics cards in home computers.
Wow, okay, that is a huge claim.
It is a big claim. But if you look at the sources we've pulled for this deep dive, the technical breakdowns, the white papers on architecture, they all point to one single massive reality. The era of raw speed is over. We are firmly entering the era of specialization.
So today, our mission for you, the listener, is to decode this. We're calling it Chips 101. We are going to figure out what is actually happening inside that tiny piece of silicon, why your next laptop or phone might actually need a completely different kind of brain, and crucially, how to spot the difference between a legitimate hardware upgrade and just an AI sticker slapped on a cardboard box.
And to do that properly, the first thing we have to do is stop thinking about chips as brains. It's just a bad analogy.
Wait, really? I thought you loved the brain analogy for computers.
It's just too vague. The sources we're looking at use a much better model that I think really clicks once you wrap your head around it. Don't think of a processor as a brain. Think of it as a factory.
Okay, I'm with you. A factory floor.
Right. And inside this factory, you have workers. Those workers are your transistors. But here's the thing, just cramming more workers into a building doesn't automatically mean you produce more cars or phones or whatever it is you're manufacturing. To get real performance, you have to manage three very specific currencies: compute, memory, and bandwidth.
Okay, I think I see where this is going. Compute is the actual assembly line work.
Precisely. Compute is simply operations per second. How fast are the workers' hands moving? But here is exactly where most people get burned when they buy a new device. They buy the chip with the highest compute number, the absolute fastest workers, and then wonder why their computer still stutters when they open too many browser tabs.
Because they completely ignored the logistics of the factory.
Exactly. You ignored the memory, which is the warehouse where all your parts are stored, and even more crucially, you ignored the bandwidth.
And bandwidth is the delivery truck, moving the parts from the warehouse to the assembly line.
Spot on. It's the delivery truck. And there was a great stat in one of their architecture articles we read that highlighted this perfectly. A huge percentage of a modern processor's time is spent doing absolutely nothing. It is simply waiting for data to arrive.
That is wild. Just sitting there.
Engineers call it the memory wall. You can have a Ferrari engine on the assembly line, but if you're feeding it fuel through a tiny plastic coffee stirrer, it's not going to go fast. If that delivery truck, your bandwidth, is stuck in traffic, your expensive factory is totally idle. The highly paid workers are just standing around smoking cigarettes waiting for parts.
So when we talk about this new trio of chips, the CPU, the GPU, and the new NPU, we have to keep that supply line in mind constantly. Let's meet the management team of this factory.
Oh, stuff.
The classic, the one we all know, the CPU.
The central processing unit.
The source material calls this the general manager. Or, actually, I'd like this one even better, the master chef.
The chef analogy is perfect for the CPU. Think about what a head chef does in a high-end restaurant. They chop an onion, then they taste the soup on the stove, then they turn and yell an order at a sous chef, then they run over to check the inventory in the fridge. It's highly complex, very sequential work.
Right. They're doing one really smart thing after another. Serial processing.
Yes, serial processing. CPUs are absolute geniuses at logic and branching. If X happens, then do Y. They are designed specifically for low latency. You want the computer to react instantly to a mouse click or to open an application the millisecond you tap it. The CPU does that. But, and here's the catch, ask that master chef to chop 10,000 carrots simultaneously.
They'd probably quit on the spot.
Or it would just take them forever.
Yeah.
Because they have to chop them one by one by one. They're just one person. And that brings us to the second chip in the trio, the GPU. The graphics processing unit.
In keeping with the kitchen analogy, the source is called the GPU, the army of line cooks.
Correct. The GPU isn't one genius chef. It is 1,000 relatively simplistic workers. They aren't smart enough to run the whole kitchen or invent a new recipe, but if you shout, "Chop carrots," all 1,000 of them will chop one carrot at the exact same millisecond.
So this is parallel processing. And originally, this was invented just for video games,
Yep.
right? Because rendering a 3D screen is basically just telling the computer, hey, color this specific pixel blue, but doing it 2 million times at once.
That's exactly what it is. It's massive parallel math. But here is the incredible plot twist that basically created the modern AI boom we're living in right now. It turns out that the math required to render a 3D explosion in a video game, which is mostly just multiplying big grids of numbers called matrices, is the exact same math required to run a neural network.
Wait, really? So AI is just geometry?
At a fundamental hardware level, yes. They are both just matrix monsters. When researchers realized a few years ago that they could run complex AI models on off-the-shelf gaming cards, the whole industry just exploded. The GPU became the accidental hero of the AI revolution.
Okay, that makes sense. But if the GPU is already this math monster and it can handle AI perfectly well, why are we complicating things? Why do I need this third chip, the NPU, on my new laptop? What does a neural processing unit actually do that my GPU line cooks can't do?
It's not about what the GPU can't do. The GPU can do it all. It's about the cost of doing it.
Cost meaning the actual price of the chip.
Cost meaning energy. Cost meaning heat. Cost meaning your battery life. The GPU is a high-performance beast, but it is incredibly power-hungry. Think about it this way. Using a massive GPU to quietly listen for a "Hey Siri" or "Okay Google" wake word all day long is like using a military flamethrower to light a single birthday candle. It absolutely works, but you're going to burn the house down in the process.
And you'll drain a laptop battery in 20 minutes.
Exactly. And this is where the NPU comes in. The NPU is the specialist. It's a custom-built machine sitting in the corner of the factory, and it is designed to do only that specific type of AI math. It strips away all the general-purpose junk and graphics overhead that a GPU still has to carry around.
I want to get slightly technical here for a sec, because I think this is a really key insight from the reading. The efficiency of the NPU actually comes from something called quantization, right?
Oh, you really did the reading? Yes. This is fascinating stuff. A CPU or a GPU usually wants to be hyper-precise. It wants to calculate things to 32 or even 64 decimal places. It wants to know with absolute certainty that the answer is exactly 4.000000001.
But for AI tasks, you don't actually need that level of precision.
Right. For AI, you don't need 32 decimal places of precision just to know if a blurry picture contains a cat or a dog. You can be a little bit fuzzy.
So the NPU is actually designed to do, quote-unquote, good enough math, but it does it millions of times faster and with way less electricity.
Spot on. It uses lower precision math. We're talking 8-bit or even 4-bit math. It's technically sloppy by strict scientific standards, but it is absolutely perfect for neural networks. That is exactly why your phone can run facial recognition on your entire photo library all night long while it's charging without turning into a frying pan.
The heat tax. That was another concept in the sources that really stuck out to me. We tend to completely ignore heat as consumers, but the literature argues it's actually the main limiting factor of all our modern gadgets.
It is the hard, unavoidable wall of physics. You put electricity in, you get math out, but you also get waste heat. If a chip gets too hot, the physical silicon degrades, so the system must slow itself down to survive. That's what we call thermal throttling.
Which perfectly explains why my gaming laptop runs amazing for about 10 minutes, and then the fans sound like a jet engine taking off and the game starts stuttering.
Because the factory is literally overheating. The manager has to hop on the loudspeaker and tell all the workers to slow down before the building catches fire. The NTU is so significant right now because it generates very little heat for the amount of work it does. It essentially raises the thermal ceiling of what your device can pull off before it hits that heat wall.
Okay, so we have the Master Chef for logic, that's the CPU. We have the line cooks for massive parallel tasks, the GPU. And we have the specialist machine for efficient AI, the NPU. But we need to circle back to the biggest bottleneck we mentioned earlier, memory, the warehouse.
Right, the kitchen storage.
The breakdown here was so helpful for me to visualize. You have cache, you have RAM, and you have VRAM. Let's break those down.
Sure. Think of cache as the cutting board sitting directly in front of the chef. It's instant. The chef doesn't even have to move to grab an ingredient, but it's tiny. You can only fit maybe 2 onions on it at a time.
Then RAM is the main kitchen table.
Yes. RAM is the big prep table behind the chef. It's very close. But the chef still has to turn around, take a step, and grab things. That takes a few nanoseconds. If you are someone who has 50 browser tabs open, your prep table is completely full. So the chef has to start walking down the hall to put stuff in the deep pantry.
And the deep pantry is the hard drive, the incredibly slow zone.
Right. If your computer is using the hard drive as RAM, everything grinds to a halt. Now the third one, VRAM, video RAM, is a special high-speed prep table built strictly for the line cooks, the GPU. It has a massive delivery chute, really high bandwidth because those 1,000 cooks need thousands of ingredients every single second.
Which is exactly why video editors and gamers obsess over VRAM numbers.
Yeah.
If that specific table is too small, your incredibly expensive GPU cooks are just standing around twiddling their thumbs, waiting for textures to load.
And that's a tragic waste of your money. You've paid a premium for the fastest cooks in the world, but you aren't feeding them fast enough to do their jobs.
So let's apply all this. We promised the listener a practical way to cut through the marketing jargon when buying a new device. I'm going to throw some user profiles at you based on what we've learned from the sources. Tell me what part of the factory they should actually care about.
Let's do it.
Profile 1. Let's call them the tab hoarder. This is a standard office worker. They have 50 browser tabs open, a massive Excel spreadsheet, Spotify is playing in the background, and they are constantly hopping back and forth between Slack and Zoom.
Okay, that is a classic chef bottleneck. That person needs a fast CPU, specifically what we call single-core performance, for really snappy switching between applications. And they need a huge kitchen table. They need to prioritize RAM above almost anything else. 16 gigabytes is the absolute new minimum for that. 32 gigabytes is even better. They can honestly ignore the NPU and the GPU almost entirely.
Okay, profile 2, the digital nomad. This is someone who is maybe editing 4K video for YouTube, doing some light 3D graphic work, but they're doing all of this sitting in a coffee shop running purely on battery power.
See, that's the tricky one. That's the modern dilemma. They absolutely need the GPU for the heavy video rendering, but they also really need the NPU to handle the background noise cancellation and the webcam face tracking on their client calls, so those features don't drain the battery in an hour. And critically, this user should look for a unified memory architecture.
Like what Apple has been doing with their M-series silicon.
Exactly like that. Unified memory means the chef and the cooks share the exact same prep table. They don't have to copy data back and forth across the kitchen. It saves a massive amount of bandwidth energy, which extends battery life significantly.
Awesome. And finally, profile 3, the gamer.
For the gamer, the GPU is king. But, and this is a huge myth to bust right here, do not just look at the model number of the graphics card. Look at the wattage.
What do you mean by the wattage?
Power limits. A graphics card labeled 4070 that is only allowed to receive 50 watts of power is going to be way, way slower than a 4070 receiving 100 watts. And you also have to look at the physical cooling. If the gaming laptop is super thin and light, that factory is going to overheat and throttle almost immediately. If you want sustained performance, buy the thick laptop with the giant cooling vents.
That is painfully practical advice. Just buy the thick one.
Physics does not negotiate. You have to move the heat out of the building.
I love that. Now, I want to clarify one big point of confusion before we wrap up today. We constantly hear the media talk about training AI versus using AI. The technical sources refer to this as training versus inference. Why does the average person buying a laptop even need to care about that distinction?
Because you, the person buying the laptop, are almost never doing the training. Training is the act of teaching a model like ChatGPT how to speak English from scratch. That takes months of time and requires supercomputers the size of a warehouse.
So when a company like Intel or AMD slaps an AI-ready sticker on a laptop, they do not mean I'm going to build the next GPT-4 on my kitchen table.
No, definitely not. You are doing inference. You are simply applying the pre-trained model to new data. You are asking it to summarize a PDF you downloaded or asking it to generate an image based on a text prompt. Inference is exactly what these new NPUs are built for. They are built to use AI, not create it.
Which leads us perfectly to the future landscape of all this.
Yeah.
Why is every tech company rushing to put these NPUs into absolutely everything? I swear, I saw an article about a toaster with an AI chip recently.
Okay, the toaster might be a bit of a stretch, but the massive push for NPUs everywhere is really about two things: privacy and latency. This is what the industry calls the shift to edge computing.
With the edge basically being my pocket.
Yes. The device at the edge of the network. Think about how it works right now. If you ask a smart speaker a question, it records your voice, sends that audio file to a massive server farm in Arizona or wherever, processes it there, and then sends the audio answer back to you. That process is inherently slow, and honestly, it's a bit creepy.
Because your personal data is constantly leaving the house.
Exactly. But with a powerful NPU on your device, all of that processing can happen locally. The audio never leaves your kitchen. The facial recognition data stays entirely on your phone. It's significantly faster because there is zero travel time to a server, and it's private because the cloud isn't involved at all.
That actually feels like a weird return to the old days of computing. For a while there, it felt like our computers were just becoming these dumb terminals, just glass screens that connected us to the internet where all the real work happened.
Yeah.
But now they're becoming truly independent brains again.
Independent, highly specialized agents. That's the key shift.
So to quickly recap the Silicon Factory for you, our listener, before we go.
The CPU is your master chef. Smart, versatile, but a serial thinker. The GPU is your army of line cooks. Brute force, parallel power for graphics, and heavy AI lifting. The NPU is your specialist, using low-precision, high-efficiency math to keep AI features always on without killing your battery. And bandwidth is the delivery truck that keeps all of them fed with data.
And never, ever forget the heat tax.
Never forget the heat tax. A fast chip that's thermally throttling is a slow chip.
The biggest takeaway for me from all this research is that we really need to stop looking at gigahertz or core counts as the only metrics that matter. A balanced, efficient factory will always beat an incredibly fast factory that is currently on fire.
Absolutely. Don't buy raw specs anymore. Buy a hardware architecture that actually fits the specific jobs you do every day.
Which leaves me with one final thought to mull over. As these NPUs get more powerful and our devices become these hyper-specialized local AI assistants, the hardware is actually going to start dictating our own behavior. If local AI gets so cheap and efficient that your phone can perfectly predict and draft your emails, your texts, and your schedules without touching the cloud, at what point do we stop thinking for ourselves, simply because the factory in our pocket is too efficient to ignore?
That is a very real, very approaching question. The hardware might just shape the human.
Exactly. Something to think about. Next time you see one of those AI PC stickers, you will know exactly what is happening underneath the hood. Thanks for going on this deep dive with us.
It was a pleasure. See you next time.